Okay, now in this problem here, we're going to actually solve some real questions about a circuit. Now, this circuit has resistors that are in both parallel and series, and what we want to do, we want to ask ourselves or answer a couple of questions about the circuit, and that is, what is the current leaving the battery that's feeding the circuit? So what's this total current coming out of the battery? What's the voltage across R1? So what would the voltage be across R1? What's the voltage across R2? And what is the current through R3? So we'll call that I3 if we like. So they're the things we wish to work out. And I find that using Ohm's law, there's a way I've discovered in using Ohm's law that makes it really, really easy to solve these sorts of problems. And that's to look at Ohm's law in two different ways. Now, just to remind you, Ohm's law is the formula that relates current, voltage, and resistance. And for Ohm's law actually basically is V equals IR. Okay, that's Ohm's law, where V is voltage, I is current, and R is resistance. However, if we can think of Ohm's law in two ways, and I like to think of them as the two forms of looking at Ohm's law, there's the global version, what I call the global version, and then there's the local version. Okay? Global and local. Now, if we're looking at a specific component in the circuit, for example, let's say we just want to look at something to do with R1 here, okay? If we're looking at a certain part of the circuit, we will use the local version of Ohm's law. Okay? And the local version of Ohm's law is V equals IR, except that V is the potential difference across the component or the resistor. I is the current through the resistor. And R is the resistance of the resistor, that particular component. Okay, so that's why I call it the local version of Ohm's law, because we're actually looking at parameters that are specific to this particular resistor here. Now, on the other hand, if we need to do something which relates to the whole circuit, for example, working out the current leaving the battery which feeds the whole circuit, or work out the voltage that's feeding a whole circuit, or work out the resistance of the whole circuit, then we're going to use the global version of Ohm's law. And in the global version, V stands for the EMF, or the voltage which supplies the whole circuit. In other words, the voltage of the battery. I stands for the current leaving the battery and feeding the circuit. So I is the current leaving the battery. So I'm squeezing it in here a bit. And R is the total resistance of the circuit. It's the total effective resistance. So R is the total effective resistance of the circuit. So depending on what we're trying to find, we can use Ohm's law in its global sense or in its local sense. And we'll be using both of these in solving this problem. Okay, so let's get started. So I'll just clear that little page there. And off we go. So The first step, I've erased my values for my resistors, I think, or maybe not. So R1, we'll let R1 equal 200 ohms. R2, I'm sorry if I actually wrote them, I can't remember whether I did or didn't. Anyway, we'll just come up with these new values. R2 equals 500 ohms, and R3 equals 100 ohms. Okay? So, what is the current leaving the battery? Alright, so the current leaving the battery, well, in order to work that out, looks like we're going to be using a global version, or the global version of Ohm's law. So we know, with the global version of Ohm's law, we know that V is the voltage of the battery. Well, we've got that. We're trying to find the current coming out of the battery, and R stands for the total resistance of the circuit. Well, we haven't got that, we've got to work that out. And that's what we've been doing over the last couple of screencasts. So let's do that now. So the total effective resistance of the circuit remember, we've got to recognize which is parallel and which is series. So in this particular circuit, we can see that R2 and R3 are in parallel with each other, and they in turn are in series. Oops, try that again. They in turn are in series with R1. Okay, so the purple section are the two parallel resistors, and the pink section, they're in series. So let's work the inner triangle, sorry, the inner rectangle first. So let's work out the parallel resistors in here first. So we've got 1 on RT equals 1 on R2 plus 1 on R3. And that's going to equal 1 on 500 plus R3 is 100, so 1 on 100. So that's going to equal 1 on 500 plus 5 on 500, which equals 6 on 500. So 1 on RT equals 6 on 500. Therefore, RT on 1 is going to equal 500 divided by 6. And if we work that out, that will be 500 divided by 6, which is 83.33. So these two resistors, R2 and R3, have a combined resistance of 83.33. Now, because they're in series with R1, we can simply, to work out the total resistance, it'll be R1 plus 83.33, because R1's in series with the other two resistors. So the total total resistance of the circuit will equal 83.33 plus R1, which is 200. So that will equal 283.33 ohms. Okay, so there's our total resistance of the circuit. So we'll just write that up here. Total resistance of the circuit is 283.33. Yep. Okay, so now I'm going to 283.33, delete that. So okay, so now we know the total resistance of the circuit. We can now work out the current of the battery using the global version of Ohm's law. Okay, and that will be using V equals IR, sorry, get a new page. V equals IR. We want the current, so I will equal V over R, which will equal, now remember in the global version of Ohm's law, V is the voltage of the battery, so it's 12, and the total resistance is 283.33, so the current leaving the battery will be 12 divided by 283.33, which equals 0.0423. Or 0.042 amps.